Yeah, first of all, I just want to thank you very much for the invitation. And I just want to say I'm sad that I'm not in Hamburg at present. At the time when I had to make the decision, things were still a little uncertain. So I made the decision I did make. But I just want to say I really love Hamburg. And honestly, I really wish I was there now. And I also know that people are sick of seeing Zoom talks. So I appreciate whatever audience I have. So thank you for coming. So this talk, the title of the talk is some comments on CV, and there's a paper that goes with it called cross-validation. What does it estimate, and how well does it do it? This is joint work with Stephen Bates, who was a past student in our department, who's now a postdoc at Berkeley, and with Rob Tibshirani, is a longtime colleague of mine. The talk is dedicated to Leo Breiman and to Colin Mallows. And Colin Mallows is in his 90s now. He was a colleague of mine at Bell Labs, and he had a really seminal paper called Some Comments on CP. And so you'll notice my talk, I changed one letter in the title of his paper. And so we have some comments on CV. And Leo Breiman was famous for many things, and he was a good friend of mine. So is Colin. And Leo Breiman's famous for a number of things, in particular random forest, which is a very important contribution and is very popular in data science and AI today. This talk is about estimating prediction accuracy, okay? And it's one of the really important topics in machine learning, and we have a number of techniques for estimating prediction accuracy, such as cross-validation, and it goes back to the 70s. And if you do a Google search on cross-validation alone, you'll see over 6 million Google Scholar results. So estimating prediction accuracy is definitely something people have concentrated on for a long time. So this talk is going to be on estimating the prediction accuracy using cross-validation and how to get standard errors for that estimate. So here's a setting. You've got data pairs xi, yi, n observations. You have a predictive model, f hat, which is indexed by theta for some theta. You have a fitting algorithm that produces your theta hat. And then you have a loss function, which tells you how well you do when you make a prediction compared to the true response. And then what cross-validation does is you break your training data up into k folds in some fashion, usually at random, okay? So these i's, or capital I's, are sets of indices, and there may be k of them. K could be 10, and what you do is you fit your training model, so you estimate theta hat on k minus 1 of the folds using your algorithm, and then you compute the errors in the fold that was left out, okay, using your loss function, and you get a collection of errors, okay, on the holdout set. But then you do it again using another one of the fold sets as the left out set. And so you see, we put ik back in here. Now we've left ik minus 1 out. You refit your model, and you get more errors on the left out set. And you do that k times, okay? And so now what you have are E1 all the way up till En are the individual errors from the holdout folds. And now what we're going to do is compute the point estimate of the error and try and compute standard error estimate of this guy. And the point estimate is just an average of the errors, and that's good, and that behaves well under all kinds of scrutiny, right? Because it's just an average. But the standard error estimate, if we just use the naive formula, which is just take the empirical standard error of the EIs and divide by 1 over root n, which we would do for an average, then it doesn't stand up. So I'm just checking the chats to make sure people are still able to see okay. Okay. So the thing is, can we take these at face values? So part one, estimating the standard error. So this is a picture of a cross-validation plot from our package GLIMnet, where we fit in a lasso model. And on the vertical axis, you get the cross-validation error. And on the horizontal axis, you've got the log of lambda, which is the regularization. So this red curve is the average cross-validation error as a function of log of lambda, right? And the orange interval that we've plotted here is a one standard error interval based on cross-validation using the naive formula, okay? This is a simulation, and the green curve is actually, in this case, the true error, right? Based on a very large sample, because we know the true population. And so, and so it appears that we'd normally go for the minimum cross-validation error somewhere around here, but it appears that the true error is much worse, and maybe this interval is a bit. Actually, this is a two standard error. So this is intended to be a 95% confidence interval, and it seems like it's a little off, right? And here's a setup. It's a sparse logistic model, 90 samples, 1,000 features. The true Bayes error is 0.22. So the true error in this case is around about down here, right? Oh, I guess this is supposed to have 90% coverage in this case, right? So Frank Harrell raised doubts about P bigger than N machine learning results in a 2019 seminar at Stanford. And this actually got us thinking about this problem. So the point is that naive confidence intervals can fail. So here's again the formula for the naive formula for the standard error. And the 90% confidence interval, we take 1.65 on either side using the standard error estimate. Here's another simulation, similar setup, okay? And so 90% means we'd like to have 5% in either tail. So over many, many simulations, what we're showing here, so the simulations draw from this model. The x's will be different, the y's will be different, right? And so each point corresponds to one simulation with the estimated standard error. In this case, we're just using a single lambda for the lasso, but we're showing the point estimates and the standard error bounds. These are average, right? And you can see the orange is a true 90% confidence interval based on the simulation, and the green is the average confidence bound based on the cross-validation. And they're pretty badly off. They're much narrower. So the confidence interval in this case needs to be about 70% bigger to be valid. We get about 30% miscoverage. So that's the problem. So this project was to try and investigate what was going on. So I think this has been known for a long time in various forms, but cross-validation errors, in other words, that vector of n errors that we computed in cross-validation have positive dependence. And there's a paper that goes back to Bengio and Granville in 2004, but probably others have seen this as well. And so the question is, why is there dependence? And it's because of the way we do the sample reuse, right? So this is a cartoon depicting the n by n covariance matrix of this vector of cross-validation residuals. And you can see we've marked three regions. We've got on the diagonal are just the variances. In the blocks, we've got the covariance between the errors that were all measured within the same fold, right? These are each of the left-out folds. This, in this case, is 5-fold cross-validation. So they're going to be correlated because they all relied on training data. They all use training data, which has got some randomness in the k-1 folds. And so that causes correlation amongst them. And then in the blue, these are errors that correlation or covariances between errors that were in different folds. And they're going to have potentially additional correlation because their training data overlapped, and so these errors would be in the training data set for the counterpart and vice versa. So you can see there's three sources of covariance. There's the variance, the covariance between errors in the same fold, and the covariance between errors in a different fold, right? And it's not too hard to come up with this formula here, that the variance of error hat, which is the variance of the sum, has an expression like this, right? Which involves these three types of covariances, okay? And sometimes this is bigger than 1 over n times any given variance, which is the terms on the diagonal, right? But the expected value of the naive standard error that we compute by just using the usual formula is strictly less than 1 over NA. So 1 over N A1 would be the variance you'd expect for an average of independent observations, each with the same variance, right? And the true variance is bigger than that, much bigger often, but the expected value of SE hat is actually less than that. Right, so you can see we got a problem. So after lots of attempts, we came up with a way for estimating the variance without assuming independence. Okay, and again, we're going to use the k-fold formulation, but we're going to do a nested type of cross-validation. So what we're going to do is we're going to have a left-out fold. We've got the k-1 folds here, and so that's like a smaller training data set. But what we're going to do is actually estimate a prediction error using cross-validation in these k-1 folds. In fact, what we do is we do k-1 fold cross-validation here. So we're going to separately estimate a cross-validation error using this clump of data. And then we're going to compare that error to the error in the completely left-out fold. And if you do it that way, you get an identity, okay? An identity is that the expected square difference between these errors inside here and the errors computed out, right? Now, notice that these two guys are completely independent of each other. For this, we have so the identity we get is that the expected value of error in minus the true error is the expected square difference between these two quantities, which we've just computed, minus a term, which is this term is really the variance of the errors in this left out fold. Okay, so this is an identity that we can write down, and we can run many realizations of this system and get many realizations of this term and this term just by averaging. And by averaging, we don't get caught out with the correlation. The averages will be consistent, and so we can get a consistent error estimate of this term. So that's the idea. So it's a form of nested cross-validation that doesn't get killed by these correlations and covariances. So just to illustrate it a bit more, here's the left-out fold. We've got this inner cross-validation where we're going to run the cross-validation train. So this will be in the inner loop. This is going to be the left-out test set. This is going to be the training set. We're going to do that again. And once we've done it k-1 times, we get a cross-validation estimate for this inner set here. Here's the holdout set where we can compute the errors of the model using all these data over here. And then we get the identity over here. And then we use our mean squared error identity in the previous slide. And when we do that, this is the same picture I showed you before. What we find is that we get wider errors. So the picture before, the green is the naive interval. The red are the true quantiles. And when we do this nested cross-validation, we get the blue curves. And you see they have about the right width. They're a little biased downwards on the upper interval and a bit biased down low on the lower interval, but they get about the right coverage. And our goal was to try and get the right coverage. So this seems to have helped and improved the estimate. And if we go back to our picture of GLMnet, and we see the original naive 90% interval, if we use this widened interval, you can see the confidence intervals, pointwise confidence intervals have increased quite a lot, and we get, it's still not covering the true curve, but of course this true curve is just one realization, and our confidence interval is supposed to cover this 90% of the time, and in most places it does. Round about the minimum, it's not quite. Okay, so that's our procedure: 90% for nested cross-validation for estimating this quantity. So to recap, CV confidence intervals can be much too small. Sample reuse creates positive dependence, and so the standard error estimates are too small. Our proposal in this case is nested cross-validation. The estimated standard error without assuming independence takes 100 times, say, more computation, because we have to do cross-validation internally and externally as well. And when does normal cross-validation fail? It's worse when N over P is small. So if you have a small number of samples and large P, wide data, and also with less regularization. And we have a software package that implements that. So that's the first part of the talk. The next part is what is cross-validation estimating? And this has also been a sort of slippery issue, and we try and get a handle on this. So I think what we'd like to estimate is what we call error sub xy. You fit a model on your training data, and the training data is indicated by capital X, capital Y, right? And error sub xy means I want to estimate the prediction error conditional on the training data. So the idea is you're going to take your estimator and deploy it out in the real world. You fit your model once and for all on the training data, and you want to know what the error is of your model. If I had a different training data set, I'd get a different model, right? I might have been lucky and have a really good training data set. I can fit a really good model, and I can expect to get good prediction error. If I had an unfortunately bad training data set, I wouldn't expect to get such good error. I'd get worse error, right? So conditional on the training data. So that's what this notation is here. It's the expected error on an additional data point drawn at random from the population, conditional on the training data, okay? Another error, which we may consider, is the average of these guys, average over training sets. An average error, we often work with average error because it's more about a statement about the type of procedure you're using as opposed to the particular instance on these training data. So here's a result of a simulation. We've got 100 samples, 20 features, and in each instance, we've computed error sub xy. And by the way, in this case, I believe that, the x's were fixed. It was just the y's that were changed. We got error sub xy, and then we got the cross-validation estimate of the error. And what you see in this picture is they completely uncorrelated. So in this picture, we see that conditional on X, cross-validation is not able to estimate error sub xy. It's uncorrelated. So that's the first kind of surprise, right? We're not able to do it. So let's see what happens in the linear model. So this is quite a crowded slide. There's that same picture again. So in the linear model, we've got Y, we got a linear model for Y. The usual standard textbook setup, the errors are normal naught sigma squared. The xi's maybe come from certain distribution. And the theorem we have is that the cross-validation error estimate is conditionally independent of error sub xy given X. And we saw that in this picture. So that was a bit of a surprise. in handwriting here, I give a little example which makes it blatantly clear in this linear model setup. So I'm sure many of you are familiar with the leave one out cross-validation formula. It's almost like a magic formula. Leave one out that's when k is equal to n, right? So you go and you do your cross-validation, leaving one observation out, and you fit your linear model on the n-1 observations, compute the error, and do that n times. And the formula you get is, it says, well, what you can do is just compute the full linear regression on all the data. You get your y-hats on all the data, and you compute the squared error, but you have to divide by 1 minus HII, where HII is the diagonal elements of the hat matrix, right? So this is a famous formula, which tells you can do, in the case of linear model fit-in, or any model where there's a linear operator, you can get leave one out cross-validation essentially for free, right? But notice this, leave one out cross-validation, conditional on X, just depends on the ordinary residuals in linear regression. But the true error, which is error sub xy, just depends on beta hat. It just depends on beta hat. That's all you take from the training data, and you can compute the true error by taking expected value over future test points. But we know from our linear models that beta hat is independent of the residuals in this Gaussian setup, conditional on X. So in that simple case, this is a proof of the theorem. So here's another statement of the theorem. Let's suppose, here's my two co-authors, Stephen's data, he's got x1, y1 to xn, yn, and he fits the model, and we get error sub xy for Stephen, and we get the cross-validation error for Stephen using his data, right? And then Rob has the same x's as Stephen, but he has different y's drawn from the same distribution, right? And then we get cross-validation error for Rob using his data, different y's, same x's. So it turns out that Rob's cross-validation error is just as good at estimating the true error for Stephen's model as Stephen's cross-validation error is. So even though Rob has got different y's. So yeah, it was a little bit of a surprise. So there's error sub xy. This is something that we may aspire to estimating, right? It turns out that cross-validation has got nothing to say about error sub xy. What it does have something to say about is the expected value of error sub xy given x. In other words, averaged over all training y's that you might see. And down at the end of the scale here, even smaller, is the average of all of these, right? Error, which is the expected value of error sub xy, averaged over training x's and y's. This one's averaged over all training y's, but keeps the training x fixed. Of course, these are going to get smaller because of the averaging, right? I guess there's quite a few results in our paper, but the cross-validation error is better at estimating error sub x than it is at estimating error sub xy. Because there's a part of error sub xy that we don't have access to. So here's mean squared error calculations over simulations. There's the true error sub xy, and here's error sub x, and you can see they're much smaller. And but the difference, cross-validation is quite good at estimating error sub x, but it's not able to get at the discrepancy between this and that one. Okay, so there's different results. The other result that's interesting is that the overall average error is much closer to error sub x, right? And so I guess the answer is that with cross-validation, we really should think that we're estimating either the average error or error sub x, but we're not really estimating error sub xy. But it's sort of counterintuitive. Certainly it was for me, because getting back to leave one out cross-validation, until a year and a half ago when we did this paper, I would tell my class that if you're really interested in estimating error sub xy, right, what's the error for the model trained on these data that you have, leave one out cross-validation would seem like the best candidate because you're hardly changing the training data much at all when you leave one point out. And so it seems, by not perturbing the training data set too much, this leave one out would be the natural estimate of error sub xy. But we see here that, no, it doesn't have access to it. There's a general result. I mean, I was able to demonstrate it for leave one out, but it turns out that it's true for a lot of estimates of prediction error, not just cross-validation, right? And so we have a result that if your error estimate is what we call linearly invariant, right? So if your estimate of error is going to be the same if you add to your y's any linear combination of your x's, and that leaves your estimate of error unchanged, you're going to have the same property. And it turns out for many of the procedures we use that this result is true. So for cross-validation, it's true. For bootstrap, out-of-bag, 0.632, it's true. For mallow CP or ARC, it's true. And data splitting with refitting, it's true. The conclusions are the same for all of them. All are better at estimating average error than estimating the conditional error. So the third part of the talk is random forests and out of bag inference. The first statement is, I think, something that most people know, is that when you fit a random forest, the out of bag error that random forest delivers is essentially leave one out cross-validation. Random forests, the way they work, they fit randomized trees to be bootstrap versions of the n training points and average their predictions, okay? For each observation in the training set, what out of bag does is it averages the predictions from all trees growing to bootstrap samples that did not include observation I. It's about 2/3 of the trees. To create a leave one out, or what's called LU prediction, and a leave one out error QI for that observation, okay? And then, of course, you do that without any extra fitting. It's just a matter of sifting through the trees and keeping a record of who was in what fold and that was used to grow the tree. These errors are averaged for all n observation, and this gives the what's called error hat out of bag, which is the average of these QIs. But I think you can see if the number of B of trees is large, then modulo a small n versus n-1 correction, this is exactly the leave one out cross-validation estimate of error. So what goes with this statement is that with random forest, at some point when you've got B large enough, the model doesn't change much. It's, you can't overfit in random forest. So as long as you've got B large enough and your estimate stabilizes, you're done, right? So if you fit a larger number of trees, it's not going to change your random forest. It change it in small, tiny little noisy ways, but it's not going to really change the model. And in fact, you can say the true random forest is the limit as B goes to infinity, right? And in B goes to infinity case, this statement is actually correct, except there's an n versus n-1 correction. So that's a real nice property of leave one out, of error hat out of bag error for random forest, that it's leave one out cross-validation. And we saw previously that in a sense, it's leave one out. It's not really accessing error sub xy, it's accessing the average error. So now can we efficiently produce confidence intervals for error or error x based on out of bag error? And can we also efficiently produce standard error estimates for random forest predictions? And so we take a different approach here. And this is work with a present graduate student, Samyak Ranjan Rajanala, who's in our department. And it uses clever tricks from a paper by Brad Efron, Jackknife after bootstrap standard errors and influence functions. It's a 1992 paper to do on the bootstrap. Just like before, if we take the set of QI, those were the errors from the random forest, if we compute the naive standard error, it ignores a correlation of the QI. And the idea of this paper is, since the error hat out of bag is a smooth functional of the empirical distribution of the data, And so the idea is to use the infinitesimal jackknife or this ordinary jackknife to estimate the variance of error hat out of bag. So let me just remind you, we'll talk about the ordinary jackknife. So the jackknife estimate of variance of some statistic, in this case, error hat out of bag. I hope you can read my squiggly annotation here. You know, the jackknife estimate of variance, there's a standard formula for it, and it says whatever the statistic is, what you do is you compute the statistic with observation I left out. So that's what this notation means. And you do that for each observation left out. So it's kind of like a leave one out quantity. And then you compute the average square deviation between these one left out estimates from the average. And then there's a modification factor n minus 1 over n. So this is the jackknife variance estimate for a statistic. In this case, the statistic is the leave one out bootstrap. No, I beg your pardon. This is the out of bag estimate error. That's the statistic. Let me just remind you that the way we computed error hat out of bag was we used this trick that we look at along the trees, because each of the trees is grown on a bootstrap sample. We see which observations were in the sample and which weren't in the sample, right? And for the estimate for a particular observation, one of the QIs, we only average the trees for which that observation wasn't in the training set for the random forest. But we can do that twice. We can also do that in computing error hat out of bag superscript I. That means we're going to look at for pairs of observations that weren't used. And so by just looking at the matrix for each tree grown, for looking at the membership of who was in and who was out, we can, just like we can get a free estimate of error hat out of bag, we can get a free estimate of the jackknife estimate of variance for error hat out of bag. And using the infinitesimal jackknife, there's something similar. It's a little different, but it's similar. And so it can be done without any additional bootstrap samples. Typically, we'll use a larger B than we would for the ordinary random forest, but you just need to fit it once. And these are some simulations that show that the coverage that we get, we call it the delta method. It's this infinitesimal jackknife. And we see we're getting about the right coverage. The green is the naive method, and the orange is our method, and it's getting about the right coverage. We also use similar tricks to get standard errors for random forest predictions. This is actually earlier work that I did with Stefan Varga, who was a PhD student of Brad Efron a few years back, and he's now assistant professor at Stanford in the business school. And you can use similar tricks to get jackknife standard error estimates for each prediction made by a random forest using the same ideas, exactly the same ideas, right? By looking to see which observations were in the folds and that. And this is an example on the spam data set where we're estimating probability of spam. And for each probability estimate, we're showing the standard error estimate obtained using this method. And you see what you might expect when the probability estimates are close to 0 or 1, standard errors get smaller. When they're close to 0.5, which is the uncertainty region, so is the uncertainty of the probability estimates. And the red points are actually incorrect predictions. So sure enough, in the places where our estimates of the probability are uncertain, we tend to make more prediction errors, in addition to the fact that we're near the decision boundary. Yeah. Okay, so in conclusion, the talk was 3 parts. The first part was confidence intervals for cross-validation. And we talk about the problems with the naive estimate, which become worse when n over p is small and with less regularization. And we show how nested cross-validation is one way of getting better standard error estimates, albeit with a bit more work. This can be done with any estimation method. And part 2 digs in deeper to understand what is actually cross-validation estimating And we see that it's estimating average prediction error rather than conditional error, or the error of my fitted model. And the same conclusion holds for a whole variety of other estimates of prediction error. And then we show that one more special thing about random forests, apart from the fact that it performs well and that you have a free estimate of prediction error, is that you essentially have a free estimate of standard error for your predictions and for your estimate of prediction error, with essentially without additional resampling. And just end up by saying special thanks to Frank Harrell, because he again alerted us to the problems of naive standard errors. I think we kind of knew it, but it was so easy to do, we just swept it under the rug in our GlimNet package. And to Brad Efron for his contributions. So with that, I'll thank you, and I'll be happy to take questions.